some 20 minutes or so for discussion. And since you've mentioned that point, Stan, I'd like to ask, with your superconformal algebra, do you have axial vector diquarks in your proton or not?
Say that again. Do you have what in the proton? We have
with your superconformal algebra, mapping mesons to baryons to tetraquarks, etc. Does your proton have axial vector diquark content?
No. The proton is just the scalar diquark. It's color 3 bar, and it's got isospin 0 and spin 0.
Isn't the new marathon?
But that's the other had. But forgive me, the other hadrons, of course, do have all the other.
I know that this is the point. I know that your spin 3/2 baryon has axial vector diquark because that's all it can have. It can't have a scalar diquark. But the issue is with the proton, and you and I have discussed this quite a lot. The marathon data says there must be axial vector diquarks in the proton, and you won't be able to reproduce that unless you.
I remember that discussion now. Yes.
Yeah, that's right. We had this in Florence 18 months ago or so.
No, right
so
now
it's still there. It's still an issue. I need to see what's happening with axial vector diquarks in your framework.
Okay, very interesting. We do have the this result of by John Ellis and Mark Holland and myself, that you get the right chiral symmetry of the baryon wave functions. In fact, that the result is that the proton spin is carried 100% by the orbital momentum between the quark and the diquark. It's not there, and that's another wonderful result of the chiral symmetry. So I haven't thought it through for the other case, but for the scalar diquark, it works. It exactly reproduces this work I did with Ellison and Carlinger many years ago in 1988.
Yeah, so I'm confident that you recover what you did some time ago. The question I'm asking is, with marathon data, what do you do?
I had forgotten, but I think we do have the other diquarks in the delta and the other baryons, of course. So we do have a whole systematic.
You do have that. You can't do it without them.
That's right, of course.
So I would like to get back to that point, and so I would like to solve that problem one day.
Okay,
Guy, you have a comment, please.
Yes, a brief comment. Of course, there's a difference when you have q squared equals 0, then you have this strict quark diquark structure, scalar diquark structure. But at the moment you start injecting q squared into the problem, then it becomes much more complex. And
the point is that even at a hadron at rest,
and then you have a mixture of all the things. I mean, and we can reproduce.
I'm asking a very simple question. In the proton rest frame, there is Poincare covariance insists that you will have axial vector diquarks.
Well, there is not such a thing as rest frame in the light frame. There is the intrinsic.
There's always a rest frame, Guy. There's always a rest frame.
There is the intrinsic frame in the light front where p perp is 0.
So yeah, but your proton must be able to be at rest. The light front cannot prevent a proton from coming to rest. It's just a light. It's light front quantization. It doesn't stop a proton from being at rest.
If you want, well, there's a different analysis. If you are computing the spectra, or you are computing form factors and the like. And
I'm asking for a global picture. Halfpenny described a framework that presents a global picture. Rest frame, boosted, it doesn't matter. It's fully Poincare covariant. And so we can ask the question in the rest frame, we can ask the question in the moving frame. The mass squared doesn't change, and we can have a proton wave function at any frame we like. And it always is axial vector diquarks.
It is more complex than that. Because
maybe in your framework, maybe it is, but for our framework, it's not. There is a frame. I can use any frame I like because they're all related.
Because you will compute what the previous talk, you are computing effective wave functions, you are computing the eigenfunctions indeed to some Hamiltonian. And then if you just plug this into the form factors and whatever, you don't get the time-like structure.
I wouldn't try to do that.
Much more complex than that.
It's a misrepresentation. It's not what we were trying to do. I'm asking different questions. I think we're talking at cross purposes. So we can go back to the beginning and say again, even in the light front, there is a rest frame. I can consider the proton with no free momentum. It's at rest. And the Hamiltonian, light front Hamiltonian exists. You can solve the problem.
The observer is moving at the speed of light with respect to the proton.
This cannot be true, Guy. You're telling me that the light front cannot define a rest frame hadron. That can't be true.
Well, for me, it's the intrinsic frame. I don't know if Stan would like to of course.
Maybe I should.
The hadron must be able to be.
There is no rotational invariance in the light front, and the frame implies rotational invariance in the.
If the wave function is independent of the momentum of the bound state, then I must be able to boost it to the rest frame.
Sure. Of course. Can I just add? Of course, you can. The answers are independent of P plus and P perp, but you're totally free to choose P plus equals the mass, and P perp to be 0. I mean, there's no the front form answers do not depend on the frame choice. So in fact, you can choose the rest frame. It just perfectly. There's no problem. You can choose plus equal to M.
I'm happy to hear that.
Yes.
And then again, we come back to the point that in the rest frame, there are action vector diquarks in the proton. And you don't have them, and I would like to understand why not. And this is something we've got to go offline and solve, I think.
We don't have them.
But there is, if you choose P perp equals 0, then you have P plus different from 0. So this is the intrinsic frame, which is more natural to the light front, because you still have P plus different from 0.
Okay, I don't want to monopolize this, so I see Cedric has a comment. Please, Cedric.
Yes, thank you very much, Craig. Yes, I wanted to highlight something that I believe was a feature appeared through today from the presentation of TC up to the GPD model of Kepani, which is that in fact, as Hervé was mentioning, the extraction of the 3D images of the hadrons, which are actually sold at as a physics case of EIC, and EICC is going to be very difficult. And we need, if we want to achieve that, we will need really feedbacks from Continuum QCD and also Lattice QCD. Especially when we look at Kepani works, for instance, we can from that for instance take physically motivated parametrization in order to extract those GPDs, and I mean all this to say that I was quite interested. I mean, I found it interesting.
Is it just me, or can everyone not hear Cedric?
Intertwin facilities that are EIC and EICC. I don't know if everybody realized that, so I just wanted to highlight.
Let's see. Any other comments? I have something to ask Bowen if there's no one else speaking at the moment. Bowen, are you still here? Oh, very good.
Yes.
Of course, I enjoyed your presentation. What you will have seen is that many of us here are interested in pi and k structure. We've had the proton for 100 years, and we've had that as a stable target for just as long. We're just moving now into an era where we can have access to pion and kaon targets, which is very exciting. Can EICC do anything for us when it comes to probing the structure of the nature's most fundamental Nebu-Goldstone modes?
if I, let me think. If we try to do a scattering on the nuclear target, and suppose there are kind of like a pion cloud and kaon cloud near the nuclei target, we could have some access to that. If this is if this is right, this is what I can think of.
Okay, so you're suggesting that like the EIC and like JLab, you ought to be able to use Sullivan-like processes to gain access to structural properties of the pion and the kaon.
Yes, I believe that this is part of the discussion.
That'd be great. I think that's written up in the EICC white paper.
Of course,
it'd be good to see that a bit more prominent, so that we see that EICC is in the same field as AMBER, as EIC, and as JLab in probing these things.
Of course. I think is part of the mass study program, and well, of course, in my I apologize that I failed to put a slides on this issue. Of course, it is part of the program. I think I think it's absolutely interesting, and understanding. I agree. Actually, I resonate with one of the speakers. I believe in the previous talks, to understand the mass problem, we not only have to understand the proton mass, but also all the meson masses.
Yes, I think that's a key, because Neville-Goldstone modes are potentially quite special. They, in many respects, seem quite different to what you might call ordinary hadrons. And it seems to me that we are now reaching the point where, for the first time in history, we have the chance to probe deep inside them, these things that are actually unstable but can now be reached. And that's an exciting opportunity. I think we shouldn't miss that.
I 100% agree with you. I think that the mesons, they provide a different perspective to the mass problem. And yes, it is also equally important as well.
Yeah. There's another, thank you very much for that, Bowen. I wanted to come back to another point that we discussed a little bit yesterday, and the Capeny raised it again in his presentation. It was about the ordering of radii. And it might not have been evident from Capeny's presentation, but the work he described makes it algebraically clear that under very general assumptions on the form of a meson GPD, the mass radius must be less than the electric charge radius, and that must be less than the mechanical radius. And this comes in, again, as I mentioned yesterday, because of the different weighting of the probes. And when you write them in terms of the GPD, you can see in some of the formulae that might not have been in Capeny's talks directly, but in the paper he was working from, there's an extra suppression factor at large X for the mass radius. And so that's where it's coming from. And typically, under general, more particular assumptions, you'll find that the mass radius squared is about 3/4 of the charge radius squared. As I said, this is quite general. We haven't done anything for a 3-body problem yet, but the same sort of structural weighting suppressing large X inside the object will probably have the same effect. So one should expect the mass radius of the proton to be less than the electric radius for the same reasons. So I thought I should highlight that as part of the discussion we had yesterday.
Yeah, this is actually absolutely fascinating. And I have to say that I got into this problem and I was reading it only recently. I think on the other hand, the mass radius is having a large uncertainty at the moment. I guess we will have to wait for more precise data
You're absolutely right. So far as data is concerned, we can't say anything strictly yet. I'm saying that from a theoretical perspective, the algebra tells us that the mass radius must be less than the electric radius under very general assumptions on what a GPD looks like. And so I think we have you can write some pretty tight bounds. And so in a sense, this is a benchmark or a test for precision experiments. If the experiments are not satisfying these bounds, then perhaps we ought to go back and look at how the data has been taken.
Right. Actually, I have a question about this. Does lattice QCD, can lattice QCD say something about this?
Lattice QCD has some, what you might call, preliminary is not the right word, but sort of a sketch. They have sketches of what these distributions are. And analyzing those sketches, they are consistent with the statement that the gravitational, the mass radius is less than the charge radius. Again, they couldn't be otherwise because of these statements about the form of GPDs and how the integrals for the form factors are weighted by Bjorkane X. So in a sense, if the lattice is properly represented in the symmetries of QCD, then it must have the same ordering, that the mass radius is less than the electric radius, etc.
Yeah.
So, Greg, this is Rolf. Go over that again. I mean, because in principle, this could be very interesting. It's like how essentially, if you get to any state of confinement, anything coming out of the vacuum, any prison I make in the vacuum, does that directly already tell me something about these different radii? Is it more general? Yeah. That's what I'm asking.
It is more general. I'm saying that looking at what the general support properties of a GPD for a two-body system, and I'll highlight again, I haven't done this for a three-body system yet. I suspect similar arguments are valid. Looking at the general support properties of a two-body GPD, you will find that the mass radius is something like x squared 1 minus x, the expectation value, and the charge radius is x squared. And because of the extra 1 minus x suppression for the mass radius, you're going to get a smaller number. It's just about the probe, in a sense, spin 2 as opposed to spin 1. These things are weighting the integrals differently, and it's expressed in a number of ways. But the simple statement is different probe, looking at different aspects of the GPD. And so you have these bounds that you can place because of the support properties of GPDs. Is that an answer that is acceptable?
Yeah, I think so. That's mainly what I was thinking, is that if you have some QCD vacuum and you put some prison in there, can you directly already say something? And I think you answered it because it comes in more or less what probe you use more or less to get this information.
Yeah, I think that's right. I mean, for example, in another case, you can look at the scalar form factor of the pion. Again, it's a different thing. It has a different radius, but scalar probes have different support properties or probing properties to vector probes, to spin 2 probes. And so each one of them, the radii is different. And you can put orderings in place just by looking at how the probes explore the support properties of the wave function. Alexander, are you still there?
Yes, I'm still there.
I had another question, going back to some of our earlier discussion. You highlighted that it's best to use front form, and I agree with you. So I'm asking a different question. Does anyone actually use instant form for a scattering calculation? Are there people out there who are still trying to compute form factors at large Q squared using an instant form quantization scheme?
Well, all lattice calculations, for example, are in what you would call instant form.
Is that really true? They seem to be looking at Schwinger functions and just looking at ordering of operators in a Euclidean sort of time.
Mm-hmm.
I'm not sure that's quite the same thing. So that's an issue that ought to be addressed, if that's really what is being done.
Well, what I'm familiar with are calculation in the instant form that are boosted in the infinite momentum frame. And so again, those recover the front form often and not always, but that's not the way to proceed. But yeah, it's a good question. I assume that most of the calculations are made in the instant form, although of course we saw the talks and there's a lot of calculation in the front form, but I think it's still not very well used.
I think when it comes to a lattice calculation of a form factor, and maybe there's someone here who can explain it better, they have a number of problems in reaching large Q-squared that go beyond frame dependence. It's about the whole regularization scheme raising issues. So they might have some more issues, things to worry about. But yeah, the interesting thing would be to see if anyone's really doing it using instant form in any rigorous way to try and get a form factor.
Well, there are attempts to solve the light front QCD with lattice, because the lattice, apart from the fact that it's on the Euclidean in Euclidean space, it's still you know, the usual Cartesian system. But again, I'm not a specialist. That's only my understanding.
So when you're writing with Stan, you can probably address that issue a little bit and put some background in there just to be sure.
Yeah, that's a good point. Just like the pancake, and I was researching that as we were talking. Some example of phenomenology that are based on pancakes. So it's a good point.
Yeah, I think there's a lot of issues there that you raised, and few people think about them, and they ought to think about them more, in my opinion. And in those terms, then it's worth addressing them in a somewhat detailed form, so that you have the examples there and the counter examples, so that these questions are answered before they're even asked, which would be very nice.
Yeah, it's a good advice. So Craig, since I'm talking, I see we're reaching the limit, but I had a quick question regarding the last talk with the hadronic mass. The hadronic mass scale. So is this mass scale related to the directly related to the effective gluon mass?
Directly, yes. It's not the constant of proportionality is not one, but once you know the effective gluon mass, then you know what the scale is going to be.
All right. So the constant is not one, but it's not very far from one.
It's not 10 either. It's about square root of 2 or something like that. It's along those lines.
They're commensurate.
Yeah.
The reason I ask is it's to follow up on Guy's comment that the scale is very different from the scale we obtain when we do the matching of the light front holographic constant, coupling constant, and the PQCD, and we obtain a coupling of a transition scale of about 1 GeV, but those scales are defined in very different way. And if the hadronic scale that was shown at the last talk is related, is commensurate to the gluon scale, then it makes sense that it should be much smaller than the transition scale between perturbative QCD and non-perturbative QCD.
Yeah, I think that's a fair comment. Your approach to constructing the effective charge is to match the infrared and ultraviolet behavior with continuity and derivatives. We don't have a matching scheme at all. We work with continuum and lattice finger functions. And so there's no boundary, there's nothing that needs to be joined. So the scale, as you pointed out, is tied to the infrared mass scale generated by GLUE. We don't have a choice with that.
And this scale has to happen at a place where the confinement force are very strong, while our scale happen where the perturbative QCD is taking over. So that explains why your scale is much larger. So it's in my mind, just waving my hand, it's not an issue that the scale are so different, and even that's what we should expect. So it seems to make sense to me.
Yeah, that's. I think those are fair comments. What you're saying, if I just may re-express it in different words, is that your matching scale is telling us where perturbation theory and non-perturbative dynamics switches over, and ours is talking about where the gluon mass scale appears and how it begins to force the elimination of those modes from contributing to the flow of the charge. So they're quite different statements.
Right, exactly. Yeah.
All right. Thank you. Thank you very much. Everybody, it's now 11:35 here in Nanjing. Bowen probably notices the time as well. Are there any pressing issues we should address before we call it a day? Okay. Stanley, please.
I'll just add something. You mentioned before the special role of Goldstone bosons like the pion and the can and so on. Now, I just want to add to that the when you use this light front holography in the superconformal algebra and you unify mesons and baryons, you get fourplets. You get a meson, two entries for the baryon, and then the tetraquark, which is diquark, anti-diquark. But the most interesting thing relative to your previous comment is that the pion stands alone, because when you match the mesons to the baryons, it's L plus one of the mesons matches the L of the baryons. And so actually the meson, the pion, does not have a partner. So it breaks the supersymmetry between the mesons and the baryons. So it's a totally different way to think about the emergence of the Goldstone particles, that they have linear dependence. M squared is linear in the quark masses. They have no baryon partner, but every other meson has a baryon partner. And so that's another way to think about this special role of the Goldstones, is they actually break. It's the one particle that doesn't have a partner in the superconformal algebra. I just wanted to add that.
That's an interesting perspective. I hadn't noticed that in the framework you've been describing. I'll take a look at that now.
Yeah. Okay, good.
Good. Thank you, everybody. Again, tomorrow we'll begin at the same time.
Yes, Craig.
Okay, yes, I'm on. Thank you. Since we're discussing, I'd like to actually continue this discussion we're having about dynamical coupled channels work. It seems that with Harry Lee retired and also Toru Sato retired, that Argon Osaka is not going to be contributing too much anymore. Do we have an alternative? Do we have another group of people that can assume this mantle? It's a challenging task, but it seems to be crucial to make progress in this area. Does anyone have any ideas about that? Victor, Daniel, what's going on? What can we do?
I will say that people from Washington University, isn't it? What is the Michael Dorin and his group could help on this or not? I'm not sure.
Well, if you look into arXiv, at the beginning of this week, they published multiple for single pion vector production extracted in this coupled channel analysis. This is of certain help. However, of course, coupled channel analysis start with simplest channel, such as pion nucleon, and then extend this activity. I want to emphasize again, K lambda channel are located at W above 1.6 GeV and mostly, with the central part of the section, located even above 2 GeV. It is a real challenge for any coupled channel approach. So we need to think about something phenomenological parameterization. And one of such parameterization proven in analysis of experimental data is Regge theory. And here maybe Adam may add expert comment.
May I ask?
First, maybe Adam, do
you Who knows the experimental results which are the direct evidence the short-range nuclear strong interaction? Thank you, everybody.
Right, I wanted to know if Adam had some comment on Victor's statement. Maybe not, or maybe he's not here. So I see, Guy, do you want to comment or to discuss?
Yes, thank you, Alexandre. Well, I wanted to comment on Jorge's very nice talk on, particularly on slide 18, where there's the prediction for the ratio of GE over GM for the neutron. And if I recall well, this slide 18, there was there was a peak at Q square equals 6. Yes, a peak at Q square equals 6. And then zero crossing about 20 GeV square, which is a very definite prediction indeed, because there is really no data in this range. So it's a very, very challenging problem. And it's very sensitive to model predictions because, for example, in the holographic live-front QCD prediction in our paper, in fact, with Alexandre Dürr and Sabir Soufiane, which of course, it incorporates the higher orbital because it's a relativistic prediction. So we don't see this crossing neither the peak. In fact, it goes to an asymptotic value of about 0.8 at very large Q square. So this is quite challenging because this is very definite constraints on the validity of the models and especially the approximations, the truncations, and etc. So this is going to be a very, very interesting comparison of models, I believe. I'm going to put on the chat the reference to this article if someone is interested to take a look. So this is basically my comment.
Thank you, Guy, for this nice comment. Let me stop sharing. Craig, do you want to comment?
Yes, I think Guy is right. This is a very strong prediction. It is characteristic of the strongly correlated Faddeev amplitude or the Faddeev wave function for the proton. And it is going to be a test.
Am I, or I cannot?
No, someone muted me. I was just trying to say something.
Yeah.
Saying simply that JLab at 12 GeV will test this prediction. That will get to the point where they can see the peak or not. And the peak and the fall off thereafter are evidence for a strongly correlated proton wave function. or neutron wave functions, since they're related by isospin symmetry. So yes, we predict a very strongly correlated wave function with both scalar and axial vector diquarks. And this is one more way of testing that picture of the nucleon, not as something simple with just a scalar diquark and a spectator quark with it, but as a strongly interacting system with dynamical diquark substructures. So yes, the experiments will finally decide this issue, and before too long.
Thank you, Craig. I don't see any more hands, and I had a comment and a couple of questions on the Georges slide. So maybe I can just share the screen again and ask. So my comment was on the running coupling. So the comment I wanted to make was that it is true that the prediction from the light front holographic QCD that is given here in the red dashed line is extracted from an observable, just like the experimental data that are shown. But we should keep in mind that the choice of observable that is pointing out by George in the slide is it's not a specifically bad, especially bad, how to say, characteristic of this quantity, because the choice of observable is equivalent, at least in the large Q-square domain, to a choice of scheme. So extracting from experimental data or extracting an observable dependent coupling is basically the same as choosing a renormalization scheme. It's not worse than that or not better. And in fact, you can you have a theoretical relation to move from an observable dependent coupling, such as the one that is shown, to a non-observable dependent coupling in some specific scheme. So this is no more than the scheme dependence of the usual running coupling. So I wanted to make this comment. I should also comment.
Yes, Alexander. Well, just let me tell you that you are right. I mean, in that sense, you always define the strong coupling constant in a renormalization scheme. You can use the MS bar scheme, which is the typical scheme used by perturbative QCD calculations. And everyone believes that this is the true strong coupling constant at very large momentum. So, okay, let's define a different scheme. You can say this scheme is given by the experiment, and it is right in the sense that you are using a particular Jorgensen rule, in which you can see the spin-dependent structure functions of the proton and neutron. Then you can assume that you are getting a leading order and next to leading order, and you put everything in the next to leading order contribution with the running of alpha G1. Well, you have below in this slide how they compare alpha G1 with respect the prediction of Dyson Swinger combined with lattice QCD calculations about these process-independent effective charge. And what you realize, at least at very large momentum transfer, is that both are the same. Okay, we are quite comparable. But I think that we are not allowed to avoid any renormalization scheme. Okay, and we define our strong coupling constant in a renormalization in a particular renormalization scheme. Well, we can compare them because we can go from one to the another and see if they are if they coincide or they are in fair agreement. Well, this is what we are getting at the end of the day.
Yeah, and I just wanted to say that that was a very, I mean, this is a very nice agreement, and it's very pleasing. But my only point was that
sure.
Choice of observable is just the same as a choice of scheme. And maybe I should comment also that we can transform this running coupling extracting from the Bjorken sum into an MS bar coupling. In that case, the freezing of the coupling is happening at a much lower value, about half of what the freezing value for in the G1 scheme.
I think that, okay, you could. I mean, the point is that at the deep level, I will say that we are in agreement in the following sense. We are avoiding the Landau pole. We know that our running of the strong coupling constant saturates at very low momentum transfer. Then you can say, okay, instead of being pi, is pi divided by 2. It is fine from my side, I will say. I mean, I know that the interaction changes, okay? But I think that we are not in this quantitative level in order to say, okay, I'm pretty sure that the value of the strong coupling constant at q equal to 0 is, I don't know, pi, no? Well, it's okay. But at the end of the day, the message is clear. We do not have Landau pole. When we compute the strong coupling constant using non-perturbative methods, we get a saturation. And this has consequences on hadron observables, and we want to study them in that sense. But,
and I agree, and it's a good point. The message I really wanted to pass on here is that it may seem mysterious that a process-dependent extraction match a process-independent extraction, and that's why I was making the comment that process-dependent is just something equivalent to a renormalizations dependent. So it's about the same thing, and it's not that surprising in that context that there is a good agreement between the two calculations. My other question was much more general and not especially related to George's talk, but so we have seen that there's many methods to compute form factors available, and I was wondering, and it's a question especially to the theorists using Schwinger-Dyson formalism, is there any prospect to go beyond the form factor in the sense that beyond the form factor we have other global quantity for describing the baryons, such as polarizabilities and generalized polarizabilities. So the form factor, we know what it is. It's a current distribution, but we know that this current distribution will be affected by the probing photon or the probing virtual photon, and this is described by higher order quantities such as polarizabilities. And I was wondering if there's any prospect of computing them on using the Schwinger-Dyson equation. Craig, you want to answer?
Actually, I'd just like to invite Gernot to answer that because he's done such calculation.
Okay.
Yes, that's right. Hi. So yeah, we were looking at polarizability some years ago. So you can, so we know how to compute form factors from coupling one photon to the baryon, right? But we also know how to couple two photons, or in general, two currents. So we looked at Compton scattering and we extracted polarizabilities. Unfortunately, that calculation is still at a somewhat preliminary level because there are several issues in how to preserve gauge invariance if you have a truncation. So if you cannot compute all the diagrams because some of them are very complicated. So I would say that's still sort of 70% finished only, but we should revisit that at some point again, yes.
Okay, I'm very happy to hear that. And I want to point out there's a new measurement of spin polarizability from class and the whole area of Jefferson Lab. So those are the spin polarizabilities, gamma 0, and so the generalized longitudinal spin polarizability, but we have also measurement coming available on the longitudinal transverse delta LT.
Right. So 2 years ago with Gilberto D'Amalio, I started from the opposite end. So how can we use experimental data to extract the polarizability contributions in content scattering. So also for the generalized polarizabilities and delta LT and all this stuff. So we're trying to get to it from both ends.
Okay, so what I wanted to say is that there's now a complete set of data. The proton delta LT is not published yet, but it will be published probably within the year. But the only, beside models, the only calculation that are available so far are chiral perturbation theory calculation, and they really have a hard time describing those data. So it would be extremely valuable to have another approach looking at spin polarizabilities, and that's why I was asking the question. And if you did work on that, I encourage you to continue this work, because we have no success so far from the theory to describe this data.
Yeah, thanks. Very good point. We will continue that. Yeah.
Thank you. Craig, do you still have your hand up? Do you want to? Yes,
actually, I'd like to go back to the discussion of the effective charge. There's no, we don't have an ambiguity in deriving that. We actually can't get anything else. We use the pinch technique and the background field method to rearrange the summation of diagrams in the gauge sector, and that turns the gluon vacuum polarization reanalyzed in that form into a unique type of analog to the QED-Gelman-Low effective charge. So it is a unique definition of the running coupling. And what's fascinating to me is that it does look so much like the process-dependent charge that you get from the Bjorkheim sum rule. And so I like to turn it around and imagine that the Bjorkheim sum rule, for reasons related to its isovector character and other such reasons, is the closest thing we have experimentally to gaining access to this process-independent effective charge. So that's how I tend to interpret this.
And I'm on board with that. The isovector nature of the Bjorkheim sum rule essentially filter out a lot of resonance, which would be messing up the extraction of a coupling from such an observable. So I like to think of the Bjorkheim sum rule as mostly made of non-resonance, a non-resonance background, even at low Q square, and that may be why somehow it's a good way to extract the strong coupling at very low Q square. But it's not just the experimental data. There's also the light front approach, which has been very, very successful on many other observable. And just like the Schwinger-Dyson equation, there's also no freedom in obtaining a coupling from this framework that, as I said, consistently describe a lot of other type of observable that are very different phenomenology. And again, there's an excellent match between this completely constrained prediction and both the data and the Schwinger-Dyson equation. So it's a very nice convergence of three very different extraction and approach to the strong coupling at low Q square. And I share your enthusiasm with those results. Victor, you wanted to comment? Victor? You're still muted.
Sorry, yeah, I was muted. I have actually a question to you, to Craig and expert in light front. Could we see some prospect considering a very close curve from light front and from Dyson-Schwinger on the effective charge running to understand how degrees of freedom in Dyson-Schwinger and light front connected?
So I can answer from my perspective, but I'm sure Craig or Guy will have a different one. But there's a connection between the different mass that emerge, the different hadronic scale that emerge at low Q square, and I don't think it's too difficult to connect them. For example, my naive connection between the running coupling in the light front approach and the running coupling in the Schwinger Dyson approach, not specifically the one that George showed and Craig talked about, but the general framework where the coupling is not diverging, not having the Landau pole because of the emergence of a gluon mass. It's a general feature that if you propagate if you propagate a particle in a potential, but you insist for the particle to be described as a free particle, then you will generate an effective mass for the particle, and this effective mass encompass the interaction. So instead of applying the interaction as usual, you just fold it into the mass, and the mass dependence of the kinematics is reproducing the dynamics. And so you can think of the free gluon propagating into the classical potential of ADS QCD as, you force this gluon to be free, which is it means it will acquire an effective mass, and that way you can connect this effective mass that is the key parameter from Schwinger Dyson equation to the classical gluon potential, which is the parameter in light front holographic QCD, or the phenomenology of light front holographic QCD. So it's just some hand-waving explanation, but I'm just giving it as an example of how, at least for me, I don't see, I see that the two can be connected, and there's no mysterious disconnect between the two results. But certainly I would love to hear what Craig or Guy want to say about that. Guy?
Well, thank you, Victor, for this question, and Alexandre for the explanation. Well, I think that both frameworks have similar predictions but and that's very important to examine further. But I think that the most important, and where we are going to learn more, is where they disagree, because there's where we are going to understand things that perhaps we are not understanding right now. And this example with the neutron G over GM, I mean, that's a very interesting example of a simple observable, which is the elastic form factor, and see how it works there. And by the way, we are going to re-examine our prediction by including the C quarks, because this of course will have some effect, but the main result we are seeing is that we don't see this peak, and that's quite surprising. And by the way, the crossing is out of the reach of experiment right now, but not the peak. So it would be very interesting to see to measure this, and I believe JLab is going to have data. So we really need critical experiments that would guide us, because after all, those are models. I mean, models, in our case, it's a model. In the case of Dyson Schwinger, it's not a model. because it's derived from from the QCD Lagrangian. However, the actual framework of computation, yes, you have to make truncation, you have to make assumptions. In this sense, it's a model, and an experiment will see if you are doing. We have to modify some of the assumptions or include larger expansion bases. This type of things. That's my comment.
Thank you, Guy. And George, you wanted to comment also?
Yes, thank you, Stefan. Guy, just a question. What is your prediction for the protons electromagnetic ratio? It decays almost linearly with Q square. It is constant. How do you get that fall off?
Okay,
if you have it?
Yes, it is in the paper I send in the chat.
Okay.
And it is roughly the same as yours and as a, yeah. The crossing point, I believe, but I'm not sure, I have to check, but I think yours is at, what was at 10 or 11 or 12, you're crossing zero in your computation. I think ours is somewhat above that, a couple of perhaps 4 GeV more or whatever, but it is within the range. So the behavior is very similar for the proton, but not for the neutron. However, we would really want to include in the prediction the C, which we have recently used, the same model we have recently used to describe the PDGs, polarized and unpolarized for the proton. So we want to come back to this interesting problem, definitely.
If you want, I can share the paper.
I have it. I have it, Alexander, already. Thanks.
Okay. Craig?
I think, as I mentioned yesterday, we have something straight away that could be checked, and that is the ratio of F2 in the neutron to F2 in the proton. The data exists, it's just released by Marathon. And if Guy can provide us with his prediction, then we can already test where these approaches are similar and where they disagree. My guess is that Guy will produce an answer which disagrees with Marathon, because Guy does not include active diquarks in his proton wave function. So I have mentioned this yesterday. I've been chatting to Stan about this for a long time. The data is there. It's a challenge. It should be addressed. We don't need to wait to find the zero in the proton's electric form factor or the peak in the neutron's electric form factor. The key issue of whether there are scalar-only diquarks in the proton or scalar and axial vector can be tested right now because we have the data to do it. Concerning the effective charge, the degrees of freedom, there are many qualitative similarities. At the present time, we don't have quantitative mechanistic comparisons. I cannot see how to represent the running quark mass function within the holographic framework. That would be a good place to start also. Can the holography produce a running mass function to be compared with what we predict and what lattice QCD obtains? So there are many things that could quantitatively be done if we set our minds to it.
Thank you, Craig. Guy, you wanted to comment?
Yes. Well, the pictures, the frameworks, they are not identical in the way that you generate quark masses, etc. We don't have, for example, quark masses of 300 MeV. They are effective masses which are much more smaller, essentially they are saturated by the pion masses, essentially. But coming back, I am glad, Craig, that you bring this diquark, and I think my explanation yesterday was not very clear. But if you have been fighting with Stan for a long time about this, well, I think that I'm not sure if we totally agree in this point, Stan and myself. So we have really to discuss this interpretation much more. But the point is that we have the quark-diquark structure, as I mentioned yesterday, when you compute the eigenvalues of the light from Hamiltonian. However, but this means a two-body system. But for the nucleon form factor, when you have the interaction with the dress current, the situation is much more complex. And if you want to describe this by the eigenfunctions of the Hamiltonian that give you the mass, then you have to include an infinite number of states, and that's at this point is untractable. So what we do is to extend the formalism to compute the form factors, the distribution functions, etc., where this diquark concept is diluted into or is resolved into the three quark structure at the valence level, and then with the C. So we have three quarks, then the contribution from 5 quarks, etc. So we cannot really do it. We cannot maintain the diquark structure, for example, computing distribution functions, because the data does not favor that. Or otherwise, you have a very, very complex problem. So we have an effective way of describing this, which is we have found that the Veneziano type structures are predicted by holography, and they are very powerful in predicting the behavior of distribution function form factors and the like. So for F to come short, the FD over FU, or the D over U at X near to 1 in the marathon, our result is not the quark scalar diquark prediction, because, as I mentioned, the quarks are resolved in performing in the form factors and distributions, etc. So it's more complex than that. So that's my comment.
Thank you, Guy. Tobias, you had a question or a comment? Hello, you're muted. Please go ahead.
No, it's just a comment I want to make about the question of Victor. And I mean, from the 4-dimensional formulation where you have the running masses, I mean, if you build the bound state, I mean, the nucleon, or I mean, a meson, you can obtain, I mean, you have the effective charge, the kernel of your bit-salpeter equation. You can get the bit-salpeter amplitude, I mean, this was already discussed, and assess the valence light front wave function of your hadron. And maybe this is a good point to compare, because I mean, even holographic QCD, you also assess this valence wave function. And maybe with this comparison, we can see how these running quark masses and effective couplings are reflected on that, and maybe have some further insight. This is just a general comment on the point made by Victor.
Okay. Thank you, Tobias, for this comment. And I see we're running out of time, so unless there's some pressing matter we want to discuss, or if there's a special announcement from the organizer, I propose to close the day. Craig, do you want to give a final word for today?
No, I would just like to thank everybody. It's been a very useful discussion. I've enjoyed it. I'm sure everyone else has that's remained to participate. I just want to apologize that I have to leave myself. Another busy day for my family tomorrow when it's approaching midnight. But tomorrow we'll begin again at the same time with an array of presentations that will entertain us and keep us going until about the same time tomorrow. So tomorrow's beginning is the Panda experiment, and more about diquarks, more about the proton radius, and both experiment and lattice theory on nucleon form factors. So it's a good day, a good day to come back.
And we now come to the general discussion session on all the talks that we heard today, and we could also include comments and discussions on topics that we had in the previous 4 days, since this is the last discussion section of this workshop. So would you like to discuss some topics in more depth? There's actually one thing I would like to ask Daniele. Since we discussed the topic of possibilities of extending lattice calculations in the time-like region, right? And you worked with form factor data in the space-like region, right? As you nicely explained in your talk. How well-based, how well formulated would be an extension of that Schlesinger point extractions into the time-like region? Is there a possibility to get some information via this tool?
Well, I think in principle, yes, there is an info. I mean, this is similar to what we have done, for example, in the case of the spectral function of the gluon propagator, right? Where you start in the space-like region, and then you try to get what is the time-like, well, basically everything in the complex plane of this propagator. So in principle, I think it can be done, and actually it would be something that that should be done, in the sense that you can then compare with data and see how well you are extracting in the time-like region, having data in the space-like. Yes, yes, in principle it is feasible, and I suspect that you would get some interesting results and that would match the experimental values there.
And probably one wouldn't start, of course, with the nucleon, but with simpler cases, form factors where one has much more precise data.
Yeah, exactly. Yeah.
Happens. Yeah. So that could be one route to. It would also be interesting for the Panda people to have some predictions there when you go into the time-like region, right?
Mm-hmm. So, with what form factor do you have in mind exactly?
Well, I think they concentrate, or at least at first concentrate on the nucleon form factors.
Mm-hmm.
But then actually I know that in the other experiment, like the hardest experiment right now, there is some focus on the transition form factors in the strange sector, also with respect to the time-like behavior, which is then extracted from Drell-Yan processes. So I think that the general interest is mounting into these time-like behaviors.
Mm-hmm.
So I think any information from theory,
any result, yes,
of course, important and interesting there.
Okay, thank you for the suggestion. I have actually a question to Dalibor because I didn't understand his slide about the final result that he has his prediction for the radius. So, what kind of radius do you get for the proton? I mean, I missed that.
We did an isovector calculation, so it's proton minus neutron. So it's not a direct calculation of the proton.
Mm-hmm.
So what we do is we take this isovector quantity, take the PDG value for the neutron, and then infer the proton radius.
Ah, okay, so it's not a direct computation.
No.
Can you do a direct computation then?
Yes. The problem is it's more complicated because you need what is called quark disconnected diagrams. It has been done on the lattice, but they are more complicated calculations. I have to, yeah, it's a pity. Everything that's interesting is usually more complicated.
Oh yeah, that's nature, yes.
Yeah.
No free lunch theorem, right?
Yes. Yes, but I mean, you should understand my last slide in this context. You take the isovector quantity, subtract the neutron one, and then you get a value which is compatible with muonic hydrogen for the proton.
Okay, that was this 0.827 or something.
Yeah.
Yeah, plus or minus 20, right?
Yeah.
Yeah,
right.
Okay, thank you.
Yes. Mm-hmm.
Guy, you would like to contribute to that?
Yes, essentially to your question about the time-like continuum predictions, just a comment about the holographic approach, but you can take it as a very phenomenological question here, because the structure of the form factor is a Euler beta function. So it's an expansion in Euler beta functions with different coefficients that you can compute if you have some spin flavor symmetry, or you can just fit it if you want to the actual data, whatever. But then since it is an Euler beta function, the analytic continuation is trivial. Modulo that we cannot at this point really compute or predict the decay constants, the gammas. Because this type of theories are inherently large NC, and at large NC, the decay constants are zero. So, but you can, if you take a phenomenological route, to take them from PDG and then predict the time-like form factor. So we did this for the pion form factor in the time-like region, and we reproduce very well the points if you start with the data in the space light. So we will perhaps, in view of Panda, we can re-examine this for the nucleons.
I think that would be very interesting. Yes.
Yeah. There's a very simple way of computing without using dispersion relations, mainly because it has already the counting rules incorporated. Mm-hmm. Good. Mm-hmm. And when are we going to have results for Panda? How is this project going?
So the current, well, I think Ala can actually say more about that, right?
Yeah, I can say. You mean the project based? What's the timeline of the project? Mm-hmm. Well, okay, in my slide I didn't show any timeline, but in principle we expect to have proton beams for commissioning on 25. Anti-proton beams with phase 1 and physics studies are expected for 2026. Then 1 or 2 years later, well, yeah, at least 2 years later, phase 3 with high luminosity, we will have it. But before 26, we don't expect physics with anti-proton beam.
But the time-like form vectors, as I understand, are one of the projects for the Panda phase 1, right? So you will, as soon as you have the antiproton beam, you will start.
Well, originally the form factor and other object structure object are foreseen for phase 3, but some of this function can be already started at phase 1. And this is, for example, form factors. And also we are studying GDAs because the cross-section is also not so small, so we can collect few data. But for phase 1, form factor at low Q square, not at large Q square, at low Q square, where we have large cross-section close to 5 GeV square. Here we have, we can make precise measurement, yeah, but only on small region. But with muon, if we want to make precise measurement with muon at different points, we need to wait for the phase 3. But here I speak about angular distribution measurement, which means separate measurement of GE and GM. But for the effective form factor or total cross-section, this can be always extracted in the whole region because we only need the number of counts and not to make angular distribution measurements. Also, the plan is to, this is unphysical region. So we have here, the cross-section is more larger than the A plus A minus or B plus A minus. It's because Q square is small, and here we also plan at phase 1 to scan this region from the threshold down to, I think, the mass of electron per square.
Okay, so that should be very interesting. Further topics that we should discuss. Victor, again, please.
I have brief comment on the question somebody asked. How it can be that elastic nucleon form factor can change somehow, even drastically, at very small Q square. I don't know, I don't have answer, but I have some hint I want to show. Mm-hmm. Allow me to share screen.
I think you can just do that. Can you try?
So what should I do? Desktop 1?
Yes. Very good. We see your desktop, yes.
Sorry, here it is.
Yep.
What I want to show. I need to minimize somehow this. Okay, so actually we can, in principle, express elastic transition in terms of two amplitude, transverse and longitudinal. It is correct that transverse amplitude constrained by the photon point, and nothing may happen at so small Q square interval between minimal Q square achieved in Pirat experiment and the photon point. Another question, what happened with longitudinal amplitude? Longitudinal amplitude not constrained at all, because gauge invariance impose just cancellation of the virtual photon flux with longitudinal photon polarization as Q square goes to 0. What about S1/2 amplitude? We have no such information for nucleon elastic form factor, because nucleon elastic form factor, nucleon elastic electromagnetic transition expressed in terms of Dirac and Pauli form factor or Saha form factor. However, we have exactly this information for nucleon resonance electroexcitation. Here, I show you Q square evolution of S1/2 electrocoupling of Roper resonance. As you may see, no any evidence that this form factor goes to 0. Another low-lying excited nucleon state, N1520 3/2 minus, and here you may see S1/2 electrocoupling. Again, no evidence that S1 half electrocoupling approaching zero. Therefore, in order to understand this puzzle, even with ground nucleon state, in my view, it would be very interesting to explore behavior of longitudinal electroexcitation amplitude, both for ground and excited nucleon states. Still open question how to relate common Saha and Dirac form factor to longitudinal electroexcitation amplitude of the ground nucleon state. But perhaps in this way, we can get some evidence what happened at very small q square. Consider that actually all this puzzle with proton radius from optical experiment, electron shell and muon shell, come in the situation when we have no enough data point at very small q square. As soon as Pirat obtained this data point, we confirm muon radius. Therefore, in my opinion, exploration of longitudinal form factor at very low q square represent very interesting topic which may address this question.
Mm-hmm. Okay, point taken. Any comments? Okay, so that doesn't seem to be the case. Are there any further topics we should discuss before we all clock off for the weekend? No, that doesn't seem to be the case. So I would probably, in the interest of everybody, keep the discussion session today a bit shorter. We had a lot of discussions during the week. I think we had a very, very productive workshop. Let me thank you all for contributing to this workshop. It has been a great pleasure to have you virtually at ECT STAR. I would like to thank my co-organizers for organizing this event. I would also like to thank the staff at ECT STAR. I think they were responsible for setting up the webpage and processing the applications and all the things that need to be done, even with the tele-workshop behind the scenes. Daniele, you know that better than me, right?
Yes. So Michaela and Barbara, thank you.
Yeah, yeah. So you are there any more comments from the organizers, from the co-organizers, from the closing of the workshop?
I think I just want to repeat what you said, Christian and Daniela, just that we thank everybody who basically stuck with us the whole week and contributed to all the discussions, all the great talks. And I hope we continue forward with all the progress that we've seen, all the progress we identified we have to make. And then I guess I hope for myself that we can all meet face to face again soon, hopefully next year.
Next year, and then after the discussions, go for an espresso.
Exactly. All right. Yeah. Thanks, everyone.
Yes, thank you, everybody, for joining in. It's been very informative, and I've enjoyed the contributions from you all. Thank you again to Christian, Daniele, and Tanya for putting this together with me. So thank you once again, and hopefully see you all very soon in physics and in physical presence.
Okay. Bye-bye, everybody.
Bye-bye.